Hello, and welcome to Differential Equations. This is Lecture 5, Integrating Factors. Last time we saw the following theorem. If you have a differential equation, first order, with an initial condition, and f is continuous, near the point of the initial condition, then a solution to the problem exists, although we're only guaranteed existence in some small rectangle around the initial condition point. The second part of the theorem is that if you also know that the derivative of f with respect to y is continuous near the initial condition point, then only one solution exists. This time, we're going to study first order linear inhomogeneous or non-homogeneous equations. Okay, so remember that the general first order linear equation can be written dy by dt plus p of t times y equals q of t, and then with some initial condition, y of t naught equals y naught, right? So when you write the equation like this, if the function q is 0, the equation is called homogeneous. And otherwise, it is non-homogeneous or inhomogeneous. Sometimes you'll see, especially in engineering, Q is called the forcing term, right? So the homogeneous equations are equations without forcing, and then you have the equations with forcing, right? These equations are simple enough that there's an improved existence and uniqueness theorem, right? So suppose we have this first order linear equation if P and Q are continuous, on the interval AB containing the point T naught, then the initial value problem has a unique solution on this interval AB. Okay, so notice that the general theorem we saw last time, for existence, it was enough to have f continuous, but for uniqueness, we also needed the derivative of f to be continuous. Here, continuity is enough both for existence and for uniqueness. And this even better, in last class, the solution was only guaranteed to exist in some small rectangle around our initial condition point. Whereas in this case, if we have continuity on the interval AB, then we also have a solution on that interval AB. So this is a much stronger and simpler existence uniqueness theorem. These equations it's also simple enough that we can write down a solution. Right, so we'll do this using a method known as integrating factors. This is a particular case of a method we'll discuss later called variation of parameters. Okay, so to carry out this method, it's convenient to start by looking at the relation between solutions of the homogeneous and non-homogeneous equations. Right, so what's the relation? Well, suppose y1 and y2 are two solutions of the same non-homogeneous equation. Right, so that means that dy1 with respect to t plus p of t y1 is equal to q of t, and dy2 with respect to t plus p of t y2 is equal to q of t. Right? So let's think about what happens if we subtract this equation from this equation. Right? So on the right-hand side, the q's cancel, whereas on the left-hand side, if I have the derivative of y1 with respect to t, and I subtract the derivative of y2 with respect to t, I get the derivative of the function y1 minus y2 with respect to t. And if I have p times y1 minus p times y2, I get p of t times y1 minus y2 equal to 0, right? So we stare at this, and we notice that the function y1 minus y2 solves the homogeneous equation. Okay, so what does that mean? Well, this means that every solution of the non-homogeneous equation will have the form any fixed particular solution of the non-homogeneous equation plus a solution of the homogeneous equation, right? So to solve the non-homogeneous equation, all we need to do is find one solution of the non-homogeneous and then add to that all of the solutions of the homogeneous system, of the homogeneous equation. And if we do that, then we will have found all of the solutions to the non-homogeneous. Okay, so we should start by looking for the solutions of the homogeneous system, right? Okay, well, if Q is equal to 0, then the equation we're looking at is a separable equation. And we know how to solve separable equations. The general solution is y of t is equal to some arbitrary constant times e to the minus an antiderivative of p of t. Okay, great. So we've solved the homogeneous equation, and as far as the non-homogeneous, we've gotten most of the way there. We just need to find one particular solution, right? If we can find one particular solution, then that's great. We can just add the solutions to the homogeneous equation and we're done. Okay, so next we need to find a particular solution of the non-homogeneous equation. Okay, so to motivate this, let's stare at this general solution for the homogeneous system and notice that this says if you were to take the inverse of this, so e raised to the integral of p of t, and multiply that with y, you would end up with just a constant, right? So any solution of the homogeneous system has the property that if you multiply it by e to the integral of p, you get a constant. So what we want to do is think about what happens to the solutions of the non-homogeneous system if you multiply them by e to the integral of p of t. Okay. Let's go back to the non-homogeneous equation, right? So we have dy by dt plus p of t times y is equal to q of t. And let's introduce a new variable. Let's call it w of t. W of t is going to be y of t multiplied by e to the integral of p of t dt. Okay, so again, we're inspired to try this because if we were working with the homogeneous equation, then this w would be just a constant. Okay, let's see what happens in the non-homogeneous case. Okay. Differentiating w, we get, okay, dw with respect to t is equal to the derivative with respect to t of this product, right? Y of t times e to the integral of p of t, right? So by the Leibniz rule, this is equal to the derivative of y with respect to t times the integral of p of t dt plus y times the derivative of the exponential, right? Which by the chain rule is this same exponential times the derivative of the exponent, which would be p of t. Okay, so notice that we can pull out a common factor by equal to the exponential, and we can rewrite this as, let's pull out the exponential, and then we're left with dy dt plus p of t times y, right? Which is exactly the left-hand side of our equation, right? So that means I can replace this with q of t. Right, so here altogether I have e to the integral of p of t dt times q of t. Right, so we have made a lot of progress now, right? Because our equation has become, our equation for w is now just the derivative of w with respect to t is equal to this function of t, right? So now this is a really easy differential equation. You just integrate both sides. Integrating both sides with respect to t, we get, well, on the left-hand side, we're integrating the derivative of w with respect to t, so that's just w. And then the right-hand side is equal to this. So I'm integrating q of t times the exponential of the integral of p of t dt, and then plus a constant. Of course, when I integrate the left-hand side, I really get w plus a constant, but it's enough to put one constant in this equality. I don't need to put a constant on each side. Okay. Finally, since w of t was by definition y of t times the exponential, this integral of p of t, we can solve for y and get y of t is equal to e to the minus the integral of p of t dt times this integral q of t e to the integral of p of t dt plus, right, then I have this plus the constant, so I get plus constant times e to the minus integral of p of t dt. Okay, so we have found the general solution to the non-homogeneous equation, right? And if we stare at what we've just written down, we see that this is a particular solution, whereas this is the general solution of the homogeneous equation. Okay. So this gives us a recipe. Oh, actually, before I write down the recipe, let's just stare at this a moment. So one thing that might be confusing is you might think that this exponential cancels with this exponential, but they do not. They do not. So why don't they? Well, remember this notation just means some antiderivative function, right? So if we were to write this out more carefully um, as integrals with endpoints, right? Then this function you would be integrating with respect to, say, s, and the t would occur here as the endpoint. So this would be the exponential of some function of s, and this would be the exponential of that same function, but of t. And so they don't actually cancel out. You'll see this in the examples when we work out explicit examples. But I just wanted to point it out here that this generally does not cancel out with this. Okay, so here's the recipe. To solve a linear first order non-homogeneous equation. Of course, you don't really need the recipe because you have this formula. You could just plug things into the formula, and that's true. But actually, in practice, instead of using the formula, it's better to use a recipe. And that recipe is the following. First thing you do is you calculate the integrating factor. Let's call it mu of t. And the integrating factor is this exponential. Right? The exponential of the antiderivative of p of t. Then the second thing you do, you multiply the equation by the integrating factor. And recognize the left-hand side as an exact derivative, right? As the derivative of some function. That's why this is called an integrating factor, because it makes the left-hand side into a derivative of a single function. Then because the derivative is now, because the left-hand side is now the derivative of a single function, the differential equation has become trivial. You just integrate both sides. And then solve for y. Okay, so that's the recipe. Let's work out an example. Suppose we want to solve the differential equation dy by dt plus 1 over t times y is equal to 1. Okay, so we stare at this equation, and we notice that here p of t is 1 over t, q of t is equal to 1. So the integrating factor is mu of t equal to the exponential of the integral of 1 over t dt. Right, that's the exponential of the natural log of t, and so you just end up with t. Right? multiplying both sides of the equation by mu of t, we get t times the derivative with respect to t plus y is equal to t, right? And we recognize this as, okay, let's stare at the left-hand side, right? The left-hand side is the derivative with respect to t of t times y, right? Because if you applied the Leibniz rule to this, you'd have the term where the derivative hits the t, that would just be this y, and the term where the derivative hits the y, that would be t times the derivative of y with respect to t, right? And the right-hand side is just t, and now this equation is really easy because the left-hand side is just the derivative of something, so I get rid of that derivative by integrating both sides. Integrating both sides, we get on the left t times y, on the right 1/2 t squared plus a constant, and then solving for y is equal to 1/2 times t plus 1/t times a constant, right? And that is the general solution. And notice it has the form we'd expect. This is a particular solution, right? If you plug in 1/2 t to this equation, it solves it. And then the extra term is exactly the general solution to the homogeneous equation, what you would get if you had 0 here. Okay, let's solve another one. Okay, say we want to solve the equation. Now this one is an initial value problem. Let's start with e to the t times dy by dt is equal to 3 e to the t times y plus 1, and y of 0 is equal to 1. Okay, so notice that this case, right, in a previous example, the equation was given to us exactly the way we'd expect, dy by dt plus p of ty is equal to q of t, whereas this equation is not quite yet in that format. So the first thing we want to do is put it into this normal form, into the format we're used to, right? So let's put the equation standard form, right? Then the equation would look like dy by dt minus 3y is equal to e to the minus t. Okay, so that means that here, p of t is minus 3, q of t is e to the minus t. So the integrating factor is mu of t equals the exponential of integral of p, so minus 3 dt, right? So it's just e to the minus 3t. Okay, so second step of the recipe, we multiply both sides of the equation by mu of t, and we get, okay, e to the minus 3t times the derivative of y with respect to t minus 3 times e to the minus 3t times y is equal to e to the minus 4t. Okay, and we recognize the left-hand side, as the derivative with respect to t of e to the minus 3t times y. And the right-hand side stays the same, e to the minus 4t. Okay, great. So again, the left-hand side is now the derivative with respect to t of a single function. So we just integrate both sides with respect to t. Right, so we end up with e to the minus 3ty on the left. On the right, we end up with minus 1/4 e to the minus 4t, and plus an arbitrary constant. Then we can solve for y. The y of t is minus 1/4 e to the minus t, plus constant e to the 3t. Right? Then finally, we find the value of the constant using the initial condition. Right? Y of 0 is equal to 1. Right? But if you plug in 0 to this equation that we found, you get minus 1/4 plus c. So that tells us that c is equal to 5/4. And the solution we wanted is y of t equals minus 1/4 e to the minus t plus 5/4 e to the 3t. Okay. Let's work out another example. This time a word problem. Okay, suppose you have a tank which contains 10 kilograms of salt dissolved in 100 liters of water. Then water containing 0.001 kilograms of salt per liter flows into the tank at a rate of 10 liters per minute. And well-mixed water flows out at also 10 liters per minute. Right? So the total amount of water in the tank is staying the same because we have water flowing out at the same rate that's flowing in. We want to know how much salt is in the tank at time t. Okay, so let's figure out what differential equation models this situation. Let's let S of t be the amount of salt in the tank at time t measured in kilograms. Right? So the first thing they tell us is that at time 0, there are 10 kilograms of salt. Then what else do they tell us? They tell us that each minute the tank gains 10 liters of water containing 0.001 kilograms per liter salt, right? That's the same as 1/1,000 kilograms per liter salt, right? So hence, how much salt is it gaining? Well, you multiply the liters times the kilograms per liters, and we end up with 1/100 kilograms of salt, right? But also each minute, the tank loses 10 liters of water, containing, well, how much salt is in the water that's flowing out? They tell us it's well mixed. So that means that the amount of salt should be the total amount of salt in the tank divided by 100, because there are 100 liters in the tank, right? So that's kilograms per liter salt. So multiplying those numbers together, we end up with S of t divided by 10 kilograms of salt, right? So, okay, if we put those two facts together, we see that the rate of change of the salt in the tank is equal to 1/100 that it's gaining minus S/10 that it's losing. Right? We can rewrite this equation as ds dt plus S/100, that's right, S/10 equals 1/100, right? Which is, not coincidentally, a first order linear equation. Okay, so now we know how to solve these. Here, P of t is 1/10, Q of t is 1/100. So the integrating factor is mu of t equal to the exponential of the integral of P of t dt. All right, that's just 1/10, so we get e to the t over 10. Right, multiplying both sides. By mu of t, we get e to the t over 10 ds dt plus e to the t over 10 S/10 is equal to 1/100 e to the t over 10, which we recognize as the left-hand side is the derivative with respect to t of e to the t over 10 times s. Right, and the right-hand side is just 1/100 e to the t over 10. Right? Integrating both sides. With respect to t, we get on the left-hand side e to the t over 10 times s. On the right-hand side, we get e to the t over 10 divided by 10. Well, let's put the 10 first. 1/10 e to the t over 10 plus a constant. Right? So solving for s of t is equal to 1/10 plus constant times e to the minus t over 10. Right? And then in this case, we had an initial condition. Right? Because we knew that at time 0, s was equal to 10. So that lets us determine the constant. Right? 99/10. And so S of t is equal to 1/10 times 1 plus 99 e to the minus t over 10. Okay, so that is the total amount of salt at time t. One thing we can notice from this formula, of course, as time goes to infinity, this term is going to zero. This term is going to zero, which means that S of t is going to converge to 1 over 10, right? So we can interpret that as saying that in the long term, the amount of salt in the tank converges to 1 over 10, right? Of course, if all we wanted to know was the asymptotic to which the total amount of salt was converging, we could have figured that out without computing anything, right? If you just stare at the initial setup and you think about all of the water that's coming in is immediately going out, so then how much is the initial condition going to matter, right, compared to just the amount of salt in the water you're pouring in? You'll easily see that the asymptotic was something we could have figured out right away. Okay, we'll stop there and pick it up from there next time.